All right. I think this is how far I can see. Don't want to go past that squiggly line without moving the camera. Now, hopefully those of you who are now here are caught up on the lectures.
I watched half of it.
You watched half of it. Well, you'll only be halfway confused today. Because we don't have time to review all the trig that we did last time. Yes.
I missed the trig one?
Yeah, you missed the basic trig review. Because you need a little bit of trig as you do algebra. There's a kind of a little bit of a catch-22 there where you want algebra when you do trig and you also want trig when you do algebra. So which class should you do first, trig or algebra? The way we have it is you do algebra first, but then it's common in your algebra text to inject some basics of trig. So we did do a quick trig review where we went over the unit circle and the basic 6 trig functions and what radians are. All right, let's recap that really quick. What is a radian? If I have a circle with radius r, what's a radian?
How many times it takes to go over a circle twice? No.
A radian is the measure of the angle that one radius would give me. So if I picked up this radius length right here and I laid it out on the edge of the circle, it would get from here roughly to here. That's 1 radius, is that distance right there. So this angle right here is 1 radian. What's the circumference of a circle? How many radiuses to get all the way around the circle?
Pi.
Are we for real?
2 pi.
All right.
2 pi.
We'll do a quick recap. What is, I have a circle. I have a circle with a radius. What is the definition of pi?
3.14159.
I'm going to throw something at you. So this is the radius. We use c to talk about the circumference, the distance all the way around the circle, right?
Yeah.
So you know what a circumference is, you know what a radius is. What's the definition of pi? You remember?
Half the circumference times the radius.
Half the circumference times the radius gives you pi in every circle.
Circumference divided by diameter.
Circumference over diameter, for the love.
I was getting there.
Pi is equal to circumference over diameter, or 2 radiuses. Diameter is this distance, all the way across. So radius is half the diameter, so 2 radiuses gives you the diameter. Pi is circumference divided by diameter. That's its definition. Right? Really basic. You should almost be able to guess this just by looking at the picture. You already know pi is roughly 3. So you're looking for some relationship in the circle that's roughly 3. This distance is roughly 1/3 of the distance going all the way around here. Right? Just basic sanity check. Pi is talking about some sort of relationship with circles. Has something to do with radius and circumference. You should almost be able to guess it just by looking at it. But if not, fine. Once again, here's your definition of pi. Pi is circumference divided by diameter. Now, if we solve that equation for circumference, what do we get? Circumference is 2 pi r. Take this, multiply both sides by 2r. And we got this equation. Is everyone with me there? All right. So let's go back to, well, actually I need the exact circle. So here's a circle with radius r. Now imagine I took that radius, I took a string that was the length of that radius, and I started wrapping it around the circumference of the circle. How many strings of this length do I need to get all the way around the circle?
2 pi.
2 pi. This has length r. The circumference of the circle is 2 pi r. So one radius, here's my radius, one radius would give me about that far, right? Going around the circle, the distance from here to here, I'm trying to draw it so it's the same as the distance from here to here. Here's one radius. Here's two radiuses. Here's three radiuses. Here's 3.14159 radiuses. Here's 4 radiuses. Here's 5 radiuses. Here's 6 radiuses. Here's 6.28 blah 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 radiuses, or 2 pi radiuses. Right? So what's a radian? A radian is the angle that one radius measures off. This angle right here is 1 radian. If we went all the way to 2 radiuses, then this angle right here is 2 radians. Right? If I get halfway around the circle, how many radiuses does it take to get halfway around the circle? Pi radiuses. So what is this angle? Pi radians. How many radiuses does it take to get me all the way around the circle? 2 pi radiuses. Therefore, the angle all the way around the circle is 2 pi radians. So 360 degrees is the same thing as 2 pi radians. 180 degrees is 1 pi radians. 720 degrees is 4 pi radians. If you're getting lost on that, it's crucial you go back and watch last lecture. You got to get used to these radian things. They don't go away. They become more and more ubiquitous in math as you go on. So you just got to get used to them. There's no way around it. Same way you just got used to degrees. You were spoon-fed degrees for 8 years of your life, and now you're just used to degrees. Think about how random a degree is. It's 1/360th of a circle. How random is that? Why is that useful? No reason?
Just one of those things.
It's just one of those things. And yet you got used to it. A radian makes way more sense than just 1/360th of a circle. It's the arc, it's the angle measured off by 1 radius. It's much more natural units. So you just have to get used to those. Okay, so that was radians. Now, 2 important trig equations from last time. I won't re-explain how we came up with these, I'll just draw my triangle. If I have a right triangle, and it is crucial that it's a right triangle, and this angle down, so this is our right angle, and this angle right here is theta. And the hypotenuse of our triangle, we typically use an r for the hypotenuse. Because we usually draw right triangles inscribed in circles, and if we inscribe that in a circle, then this becomes a radius. That's why it's very common to use r for the hypotenuse. So if we have this right triangle, and this bottom left angle here is theta, what is the distance from here to here? What is this distance? We often refer to that distance as x. How do we calculate x? From last time, you don't remember? R times cosine of theta?
Yeah.
Coming back to you? A little bit? That's the other one you gotta get used to. And the last one, well, 2 more you have to get used to. The y we can calculate with r times sine of theta. And then finally, the slope we calculate with tangent of theta. Tangent of theta gives us y over x, which is the same thing as sine over cosine, which is the same thing as the slope.
Donnie, are those negative signs you have over there on the very left? Like negative y equals r?
No, those are just bullet points
Oh,
to
okay.
remind me. Good question. Good. Do we need to see a quick example of that? Let's do a quick example. Okay, so I'm going to give you a triangle. I'm trying to make that so that this is 60 degrees, or in other words, pi thirds. And I'm going to make the hypotenuse of this right triangle 3. Our job is to find this length right here. How do we do it?
3 cosine pi thirds.
Yes, we just type in 3 cosine of pi thirds of 60 degrees, whatever you're used to. And if you remember from the lecture I showed you, how do we calculate cosine of pi thirds? The unit circle. That's how everyone does it. So all trig students memorize that unit circle.
Yep.
No way around it. You just got to memorize it. And so, what is cosine of pi thirds? Mr. Trig student?
What?
What is cosine of pi thirds?
Root 2 over 2.
No.
Root 3 over 2.
No.
1/2.
There you go. Has to be one of those three, right?
Yep.
So cosine of pi thirds is 1/2. How are we calculating that? I showed you how we came up with these calculations last time. It takes some simple geometry to do it. So just simple geometry is how we calculated this. But after that, it's just a memorized value. So cosine of pi thirds, if you plug that into your calculator, it spit out 1/2. Or cosine of 60 degrees, you plug that into your calculator, it spit out 1/2. So this is going to be 3/2. And then this right here, you calculate with 3 times sine of pi thirds. And what's sine of pi thirds?
Root 3 over 2.
Root 3 over 2. So this is going to be 3 times root 3 over 2. So 3 square root of 3 all over 2. And then finally, calculating the slope of this thing. What is the slope of this equation? Well, now you have rise over run. So you can calculate it that way if you want. Or you can calculate it by calculating the tangent of pi thirds. Oops. And the tangent of pi thirds is equal to just root 3.
Root 3.
Uh-huh.
I was getting there.
Well, it's either 1 over root 3, 1, or root 3 for your tangent, right?
Mm-hmm.
Or root 3 over 3, 1, root 3, if you'd rather say it that way. Okay, so that's using these basic trig functions. So there's 6 trig functions that we talked about: sine, cosine, tangent, cosecant, secant, and cotangent. The other 3 I said we hardly ever use. And they're just reciprocals of the ones I already told you. Again, if any of this is throwing you off, just go back and watch that lecture again. It's huge that you get the basic trig. But the good part is that's all the trig you need to get for this whole course. It's not that much. Okay. So that was a quick review of the trig we did last time. Now, today we're going to be moving off to graphs, functions, and linear functions, or linear equations. So first off, let's start off with a graph. What is a graph? The graph, or locus, same thing. Graph, locus, same thing. Locus is set of points satisfying a condition. The graph of something is the set of points satisfying some condition. So the graph or locus of an equation is a set of all points whose coordinates, x comma y, satisfy the equation. So you're given some equation, the set of points that satisfy that equation, we call the graph of that equation. And we talked about that a bit already. So a graph is equal to the solution set. When you graph some function, you're graphing all the points that give a solution, or you're graphing the solution set, the set of all solutions. That's what you're doing. And then our last little note is, what do we mean by a linear equation in 2 variables? A linear equation is an equation where the x is to the power of 1 and the y is to the power of 1. A, b, and c are any constants. So as long as you have some constant times x to the power of 1, plus some constant times y to the power of 1, plus some constant equals 0, if you can write it this way, we call it a linear equation. Question, is this a linear equation? X equals 2.
Yeah.
Yeah? No?
It is.
Let's see, can we do it? Let's see, replace my a with a 1, so we have 1x plus 0y minus 2, or plus negative 2 if you want to think about it that way, plus negative 2 equals 0. This says the same thing as this, right?
Mm-hmm.
So any equation I can write this way is a linear equation.
What if there's a z in it? And
So-
3 variables.
3 variables, then it could be a linear equation in 3 variables. This is a linear equation in 2 variables.
Okay.
We won't do a lot of things in this class with 3 variables. We'll typically limit ourselves to 2.
So how do you get an equation that's not linear? What's an example of this?
X
Yeah,
is
it's
to an
exponent.
exponent that's not 1.
Okay.
And we'll see plenty of those. Okay, so let's get sense now for graphing some of these. I think you guys are already pretty familiar with the concept, but let's make sure. So we'll start with this equation. 3x minus 5y equals 15. Everyone understand the equation that we're graphing?
Okay.
Okay, so how do we typically do this? You make one of these little t-charts. You pick values for x, find their corresponding values for y, plot the points. And then see if you can notice a general pattern. So, typical good point to start with for x is like a 0. So if I plug in 0 for x into this equation, what do I get?
-3.
If I plug in 0, I get negative 5y is equal to 15. And so what does y have to be? Negative 3. If negative 5y is equal to 15, this is when x is 0. So when x is 0, so plug in 0 to this equation, then this whole term goes to 0. So we have negative 5y is equal to 15. Divide both sides by negative 5, and we get y is equal to negative 3. Right? So it's negative 3. And in case I lost you in what we did there, notice what happens when you plug these numbers back in, it makes the equation true. If I take 3 times 0, and I minus 5 times negative 3, what does that equal? 15. So plugging in 0 and negative 3 for x and y satisfies the equation. Notice that plugging in 0 and negative 4 does not satisfy the equation. It's not the case. So this will not be a point. So we found the point 0, negative 3. When we plot that, remember this is how far we are from the y-axis. We go 0 from the y-axis, we go negative 3 from the x-axis, and that puts us right here, our point 0, negative 3. All right, let's try another one. Let's plug in x equal to 1. What do we get?
Negative 20.
So, when we plug in 1 here, then we have 3 minus 5y, plugging in 1 for x, is equal to 15. Or we get negative 5y is equal to 12. Or we get y is equal to negative 12 fifths. So, negative 12 fifths is our answer there. And negative 12 fifths is just a little bit more than negative 2. So negative 2 is right there, negative 12 fifths somewhere down here. All right, let's pick a number that will be better. Let's pick x equal to 5 now. So when x is equal to 5, what do we get?
Y is equal to 0.
Y is equal to 0. Because 3 times 5 is 15. 15 minus 5y equals 15. Subtract 15 from both sides and we get negative 5y is equal to 0. Or in other words, y has to be 0. Follow that? So that's how she got 0. So 1, 2, 3, 4, 5, and 0. And then let's see, what else will be a clean number? Negative 5? So we'll plug in negative 5 really quick. 1, 2, 3, 4, 5, oops, negative 5 up here. So when I plug in negative 5 for x, what do I get? Negative 5 plugged in for x, 3 times negative 5, that would be negative 15 minus 5y is equal to 15. Add 15 to both sides, and we get negative 5y is equal to 30. Divide both sides by negative 5, and we get y is equal to negative 6. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. So about right there. And we can keep plotting points, and we notice that all the solutions seem to make a line, even though my picture's lined a lot, sorry. If we were to plot them all perfectly, then we notice that they all fall on this line. And so this equation, its graph, would be this line. And if I were to pick any random point on this line and go back and plug it into this equation, it would work. If I were to pick some random point not on this line and plug it into this equation, it would not work. So for example, if I go plug in 1, 1, 1 for x, 1 for y, the equation is going to be false. When we plug in 1 for x, we get 3. When we plug in 1 for y, we get 5 here. 3 minus 5 equals 15. No, that's not true. So this point 1, 1 is not on the line. The line is a set of all the points that satisfy that equation.
Is that the definition of the line
No.
on the graph?
No. You don't define a line. Sometimes. Depends on your geometry, but a line is a geometric concept. It's not something we're defining in algebra. So it's expected that you already know what a line is. Okay, so that was the first equation. Let's graph this next one now. Get a feel for it. So this next equation, we're looking at x minus 8 is equal to 0. Right?
Okay.
So x minus 8 is equal to 0. Let's see, if x is equal to 1, what's y?
X can't be 1.
X can't be 1. There is no y. If x is 1, then you get 1 minus 8 equals 0. Is that true?
No.
No, that's never true. What does x always have to be?
8.
8. So if x is 8, what's y?
Any number.
Anything. We can have x is 8, y is 1. We can have x is 8, y is pi. We can have x is 8, y is 27. We can have x is 8, y is negative 2,741. Right? All we care about is x is 8. So if we come and we draw the graph of all the points there, let's see. 8, 1, 1, 2, 3, 4, 5, 6, 7, 8. 8, 1, that's right there. 8 pi, that's somewhere right there. 8, 27, somewhere up here. All are negative, somewhere down here. And if we plot them all the points, we find out that it's this vertical line. And so, you'll notice now why we call these things linear equations. We call this a linear equation because its graph is always a line. That's what it means to be linear. Okay, now let's look at one more. One that's a little bit more strange, and see what we can make out of it. Alright, so we have y minus x squared plus 2x plus 1 is equal to 0, I am imagining. I think I forgot my equal to 0 over here. Equals 0. Okay, so let's start with picking x to be 0. What's y? So then we have y minus 0 plus 2 zeros plus 1 is equal to 0.
What?
So when x is 0,
So y plus equal sign, duh. Very smart.
when x is 0, sorry.
Okay.
When x is 0, y is negative 1, right?
Yeah.
Okay, let's pick another one. Let's try x equal to 1, see what we get. So with x equal to 1, we get y minus 1 squared is still 1, plus 2 times 1 is just 2, plus 1 is equal to 0. So what does y have to be?
Negative 2.
Negative 2. The negative 1 and 1 cancel out, so we need something to cancel out with the 2. That's y equal to negative 2. So far we found 0, negative 1. And then we found 1, negative 2. So this is probably the equation of a line slanting like this, right?
Sure.
Sure? Maybe? Let's keep trying. Let's plug in negative 1 for x, see what we get. So we have y minus, what's negative 1 squared?
1.
1. So y minus 1, 2 times negative 1 is minus 2, plus 1, is equal to 0. What does y equal?
2.
2. So when x is negative 1, y is equal to 2. Uh-oh.
See a beautiful line shown there.
That doesn't really seem to be looking like a line, but who knows, maybe my picture's lying. Probably shouldn't read too much into it. Oops. What did we get? 2?
Yeah.
So negative 1, 2. Alright, let's try plugging in x equal to 2, see what we get. So when I plug in 2 for x, we have y minus 2 squared is 4, plus 2 times 2 is 4, plus 1 is equal to 0. What does y equal?
Negative 1.
Negative 1. What the? So it's like it was going down and now it decided it's going up. Let's try one more. So here we got negative 1 again. Let's try y equal to 3 and see what we get. Or x equal to 3. So we have y minus 3 squared is 9, plus 2 times 3 is 6, plus 1 equals 0. And what does y equal?
2.
2. Right?
Yeah.
We have negative 9 plus 6 leaves us negative 3, plus 1 gives us negative 2, so we need 2 to get to 0. So at 3, we now have 2. Okay, so now you see that we have some symmetric shape coming up, and if we continue this process forever, we would see that we get a shape called a parabola, which looks something like that. So this is not a linear equation, its graph is not aligned. So we're going to notice that all linear equations, graphs, look like lines. And if its graph looks like a line, then our equation has to be a linear equation. We'll see it's a one-to-one relationship between the two. Any questions on any of those examples? Good intuition for what we mean by linear equation? It looks like this, and its graph looks like a line. Okay, cool. Now we'll put that on hold for just a second here and talk about one of the things we always talk about in every math class, a relation. How many of you have come across a relation before?
Probably.
You for sure have, but you guys don't remember what it is. Okay. So what's a relation? A relation is just a set of ordered pairs. That's it. A set of ordered pairs. Take a set where everything inside the set is an ordered pair. An ordered pair just means parenthesis, something, and parentheses. So two things inside of parentheses. Doesn't matter what those two things are, but if it's two things inside of parentheses, it's an ordered pair. A relation is a set of ordered pairs. A set where everything inside of it is an ordered pair.
Okay.
So we can have the set containing the ordered pair 1, 2, square smiley face, 1, 5, 2, 7. Perfectly valid relation. Alright? What about this set? Is that a relation? No, 1 is not an ordered pair. The first thing in the set is not an ordered pair. That's not. So it's not a relation.
Ordered pair is only 2?
Yeah, pair means 2. Ordered means it's in parentheses rather than set. So an ordered triple would look like this. So yeah, ordered pairs, pair meaning two things in there, and ordered meaning we're using round braces rather than these curly braces. Okay, another question. Is this a relation?
Yeah. Yes. 0 ordered pairs.
0 ordered pairs, you think that's a relation?
0.
Is everything in here an ordered pair?
Yeah.
Yes.
By default.
Show me one thing in there that's not an ordered pair. There's nothing in that set. So everything in it is an ordered pair.
So it's vacuum.
Everyone living in the center of the sun is Asian. No one's living in the center of the sun.
As far as we know.
We're quite sure. All right. So, ordered pair. Now, what is a function? A function is just a special type of ordered pair. Or a special type of relation, sorry. So here's a relation. A function is a special type of these relations. In other words, every function is a relation, not every relation is a function. So a function is going to be a relation that satisfies some condition. Right? Just like a man is a human being that satisfies some condition. A man is a subset of human beings. A function is a subset of relations. Every function is a relation, not every relation is a function. Alright, what's the condition that it has to satisfy? So a relation, so what's a function? A relation such that each left-hand element, when we say left-hand element, we mean each one of these, 1, square, 1, 2. Those are our left-hand elements in this example. Each left-hand element pairs with a unique right-hand element. For every left-hand element, we have one and only one right-hand element. And another way you might have heard it is every input has a unique output. So let's make sense of that with this. Let's look at this relation here and tell me, is this relation a function?
No.
This relation right here, he's saying it's not a function. Why not?
Because 1 has 2 and 5.
Yeah, because I have 1 paired with 2 and I have 1 paired with 5. So that is not a relation. Let's look at this relation here, f. F is equal to this relation. Is this a function? We have 1 paired with 2, 2 paired with 2, 3 paired with 3, 4 paired with 3. Is that a relation?
Yeah.
Or is that a function, I mean? It's obviously a relation. It's a set of ordered pairs. Is it a function?
Yes.
It is?
A unique right-hand element. Yeah, that's a function. Right. Yes.
Are we positive that's a function?
Yes.
She sounds pretty sure.
You wouldn't give us 2 wrongs. Well,
Yes, that is a function. Every left-hand element is paired with a unique right-hand element. It doesn't matter if the same right-hand element shows up multiple times. Right? Nothing wrong with that. So you got the right intuition there.
oh, so it's like the vertical line test.
The vertical line test is a pictorial way, or a geometric way, of testing if a function, or if a locus is a function. If a graph is a function. Locus, the set of all points satisfying some condition. If it's representing a function. So yeah, that's another way that you do it. Okay, let's look at G. 1, 2, 2, 3, 3, 4, 1, 3. Is that a function?
No.
Nope.
You didn't just believe them?
Bunch of sheep.
It's not a function.
It's not a function? Why not?
Because 3 leads to 4 and so does 2. I mean, wait.
We're looking at this one.
Oh.
Is that a function? Did you say no or yes? No. Why not?
So 1 leads to 0, it also leads to 3.
Yeah, one's paired with 2 and one's paired with 3. We do not have each left-hand element is paired with a unique right-hand element. Those are different. We have one's paired with 2 and one's paired with 3. So is G a relation? Yes. Is it a function? No. Relation, set of ordered pairs. Function is a set of ordered pairs satisfying this special condition. Don't get confused by those two words. All right, let's try this one. H. Is H a function? You say yes? What do you think, Celesta? We have one showing up here, and we have one showing up here. Isn't that a problem? Why not? Because they're both paired with 2. That's correct. That's a good enough way to think about it, and your intuition's good there. Those of you more comfortable with sets, what do we know about sets? Repeats don't matter in sets. And so this set is actually identical with the set just containing 1, 2, comma, 2, 1. So this set is identical to this set. So a trick question I would ask my discrete math students is, what's the size of this set? And they might say 3, when really it's 2. There's only 2 things in here. There's that thing in here, and there's that thing in here, and that's it. So whichever of those help you keep it straight in your head is what it is. Okay, now here's how we can write out functions. It's very tedious, though, to write out functions like this. Imagine that I want to write out the function following some pattern, where 1 goes to 1 squared. So we have 1, 1. 2 goes to 2 squared, or 2, 4. 3 goes to 3 squared. 4 goes to 4 squared. And I want 5 to go to 5 squared, 6 to go to 6 squared, and I want 0 to go to 0 squared, and I want pi to go to pi squared, and I want 1/2 to go to 1/2 squared. And I want to write out this infinite function. How am I going to write out all those elements? Well, we can go back to our set builder notation. I can say f is equal to the set of all ordered pairs xy such that y is equal to x squared, such that our right-hand element, y is our right-hand element, is equal to our left-hand element, x squared. Right? And now if we were to write out all the elements in here, we'd start writing out like this. And here's a way that we can represent infinite elements in there. Now we write functions out like this so often that we create shorthand for writing out this even. Even though this is shorthand for this, we even come up with shorthand for this. Because this gets tedious. And so we write this. We say f of x is equal to x squared. Where f of x is stand-in for the right-hand element. The right-hand element is equal to the left-hand element squared. And you're used to taking functions like that, and you're probably already used to thinking about a function like that as y equals x squared and calling those the same thing. This y equals x squared, that comes from this or this. They all say same thing. So when you say the function y equals x squared, what you are saying is that we're talking about this function f such that xy satisfies the condition y equals x squared. That's what you meant when you called that thing a function. Because before it was just an equation. Right? So technically that's just an equation. Now we're going to be lazy and call that a function. Is that really a function? No, this is a function. We're going to use this as shorthand for this. And so anytime I say look at the function y equals x squared, what I really mean is we're talking about this, but it's kind of tedious to write that out every time. Make sense? And another way we'll often write it out is this. F of x is equal to x squared. Now this f of x is equal to, let's say it like this, just get us comfortable with this notation. If I say f of a is equal to b, that's identical to saying that the ordered pair a comma b is in f. That's what that means. So let's give an example getting comfortable with this notation. So let's say f is equal to this set. You with me? So now, if I say what's f of 1 equal to?
2.
It's equal to 2. Because 2 is the thing on the right-hand side of 1. 2, 1. When I say f of 1 equals 2, that is identical to saying that the ordered pair 1 comma 2 was in f. 1 comma 2 is right there. Or the right-hand element of 1 is 2. The right-hand element of 1 is 2, or 1, 2 is in our function. Does that make sense?
Yeah.
Going back down to this equation, if I told you that we're looking at the function f of x is equal to x squared, and I were to ask you something, what is f of 2? What would you tell me?
4.
4. You've been doing this already, right? Is that completely new? Right, so you plug in, so f of 2 equals 4. What does that mean? That means 2 comma 4 is inside f, inside your function. F was the ordered pairs right here. 2 comma 4 is in there. It's right there. Good? Let's try a couple more with this notation. Looking at these right here, F, G, and H. What happens then if I ask you for G of 1?
2.
G of 1 is 2?
Oh, it's 3.
It's not.
Doesn't make sense. So this notation only makes sense with functions. G here is just a relation. It's not a function. So this notation doesn't make sense for G. This notation only makes sense for functions. G is not a function. It's just a relation. However, if I come down and I say what's H of 2, what's the answer? 1. Or in other words, 2 comma 1 is an element of H. That's what that means. Does this make sense? More examples, or you think you got it? You got it? All right. Let's move on then to domain and range. Domain and range. Pick some function, like f. The domain of f, which we usually represent with capital D, is the set of all left-hand elements. So the domain, if we're talking about the domain of f, maybe put a subscript f here to remind us that that's the function we're talking about. The domain of f is equal to, let's look at all its left-hand elements. It has a 1, it has a 2, it has a 3, and it has a 4. So the domain of f is a set 1, 2, 3, 4. Let's look at its range, the range of f. The range is a set, and I'll also sometimes probably say the image. I'll try to remember to say range, but might accidentally say image. The range of f is all the right-hand values. So what's the range of f? 2?
3.
Huh?
2 and 3.
And 3. And now you already notice something very strange. The domain and the range do not have to be the same size. Make sense? Okay, let's try another one. What's the domain of h? 1, 2. What's the range of h?
Also 1 and 2.
Also 1 and 2. So the domain and range can also be the exact same. Alright? Now let's take f here. F is this, which is this, right here. What's the domain?
X. Or what is it for x?
What are all the left-hand values?
X. Anything.
Anything. Any real number.
Size.
Not x, r. All real numbers. X is a variable. So the domain, in this case, is every real number. What about the range? What's the range equal to?
Numbers greater than 0.
Huh?
R.
Not r. I can't get negative 2 to come out. What's the x that spits out negative 2?
And
What number squared equals negative 2?
root of 2i.
Oh, we're not going to use complex numbers. Understood that we're talking about real numbers. Sorry. From here on out, probably make this pretty clear in this class, because we did do complex numbers kind of early. From here on out, unless specifically stated, it's understood that we're always talking about real numbers, unless we say otherwise.
Okay.
Okay? So everything we're talking about, always and forever, just real numbers, unless otherwise specified. So what real number squared gives me 2? Or gives me negative 2?
There is one.
There isn't one. So if I have x squared is equal to y, or y equals x squared, then the range is going to be all the numbers from 0 to infinity. Have you seen that notation before?
With the parentheses and the brackets.
Uh-huh. No? This means, this is shorthand for all the numbers x such that x is less than or equal to 0 and is less than infinity. Oops. So all the numbers, sorry, greater than or equal to 0. X is supposed to be in the middle. Don't let me write nonsense up there. X is in between 0 and infinity. That's what this means. Including 0. That's why we put the square there. If we didn't include 0, we would have done this around bracket, and that would have been like that. If we include 0, we put a square bracket, and that's the same as making that less than or equal to. That makes sense? So that's what that notation means. So our range is non-negative numbers, but our domain is any real number. Domain, range. Okay, independent variable, we call x the independent variable, and we call y, or f of x, the dependent variable. Good? And we already talked about that notation. Okay. That's all clear, then we'll move on to some examples. Examples of multiplying, adding, and dividing functions. Okay. So we've got our function f of x, we got our function g of x, right here. Let f of x be this thing, g of x be this thing. Our job is to find f of x plus g of x. Well, that's pretty straightforward. You just plug it in exactly how you think. First write f of x, which is x squared plus 1. And then write plus g of x, which is 2x minus 5. And And then you can combine this exactly how you expect. And so when you add it all together, we're just going to have x squared plus 2x. And then we have 1 here, and then we have minus 5 there for a total of minus 4. So f of x plus g of x is that new function. So you can add functions together to get new functions. You can also multiply functions together to get new functions. Let's look at that. So let's look at f of x times g of x. Here's f of x, x squared plus 1. Here's g of x, 2x minus 5. And we can multiply them together to get some new function. And how do you do that? Exactly the way you already know to multiply these. You distribute through. So we get 2x cubed. We'd have plus 1. Sorry. Let's see. 2x cubed minus 5x squared plus 2x minus 5. And that's how you multiply functions together. And how do you divide them? Same thing. So we have x squared plus 1 over 2x minus 5. And not really much more we can do with that. Okay? Solution functions. Solution functions, this is going to sound like a lot of messy language, but basically when you're given something with x and y's equals to 0, you can typically solve it for y equals some function in terms of x. That's all it means. When you're given something and you solve for y, you're finding what we call the solution function. So we'll go through the dense terminology, then we'll do an example and you'll say, oh, duh. So let h of xy, so now h is some function with x and y as inputs. That's what that means. And so it's just some expression that has x and y's in it, like this. Here's h of xy, for an example. So let h be some expression with x and y's as variables, where it's equal to 0. Then y equal to some function just in terms of x is a solution function, provided that whenever y equals f of x, then h of xy equals 0. So now we'll come up with a quick example, and then you'll see how this is simple. So let h of xy be the expression 3x minus 15y minus 15, and we'll set that equal to 0. So we have some expression in terms of x and y is equal to 0. Here's the expression. You with me? Solve for y. So I'm going to move y to the other side. So I'm going to get 15y is equal to 3x minus 15. I just added 15y to both sides of this equation. You with me? Divide both sides by 15, and we get y is equal to 1/5 x minus 1. There's our solution function. Anytime this is true, then this is true. That's all it's saying. So if you can find y equals some function in terms of x, y equals some function in terms of x, where anytime that's true, then your initial expression is true, then this is equal to this, then you find your solution function. It sounds complicated, but what is it really? Just solve for y. Take some expression with y's and x's in it, solve for y. Or you can also solve for x and call that a solution function for x in terms of y. Typically we solve for y and call it a solution function for y in terms of x. Okay. Now, sometimes that's not so straightforward. And sometimes you'll get more than one solution function for the same variable. And so let's see an example of that. So we have x squared plus y squared equals 25. And we're going to solve for y. So first thing I'm going to do is I'm going to move the x squared over here. So then I'm going to get y squared is equal to 25 minus x squared. Then what do I do?
Root both sides.
Take the square root of both sides. So then I get y is equal to plus or minus the square root of 25 minus x squared. And so now we have two solution functions. We have y is equal to positive square root of 25 minus x squared, and we have y is equal to negative square root of 25 minus x squared. You with me? Or in other words, for every x that you choose, we're getting 2 y's as solutions. Let's draw a table for this thing real quick, get a feel for it. So here's our x, here's our y. Let's start by plugging in 0 for x. What do we get?
Plus or minus 5.
You see how she's doing that?
Yes.
Plug in 0 for x here. We have 25 minus 0 is 25. Square root of 25 is 5, plus or minus 5. Or you could have come up to our initial expression and that would have worked as well. Plug in 0 for x squared here, and you get y squared is equal to 25. Or in other words, y is equal to plus or minus 5. Right? So let's draw a picture of this really quick.
Does that break the
And we'll just call these 5s. Huh?
Does that break the definition of function? Because it has to be.
It's 2 functions.
I mean,
I'm writing 2 functions in one line.
can you
We
write?
have the first function, y is equal to positive, the square root of 25 minus x squared. And second function, y is equal to negative, the square root of 25 minus x squared. So we're doing 2 functions in one go.
Okay.
So we have 2 solution functions. So that's why I meant by this example is sometimes you don't just have one solution function, sometimes you can have multiple. Like y equal to plus or minus the square root. So y has 2 solution functions here.
But each x only gets one y.
But each x only has one y? No, we could have also solved for x, and we would have found x is equal to plus or minus the square root of y squared minus 25. And so we could have picked our y and found our x instead.
You're saying 0 is equal to 5 and minus 5.
I'm saying at 0,
Or you get 5 and minus
we get a 5, and at 0, we get minus 5. So at 0, we get a 5, this point's on it. And at 0, we get a minus 5, this point's on it.
And so that's just saying that no other x can have minus 5 or 5.
Anytime x is 0, then y is either 5 or minus 5.
Yeah, but every other x cannot have 5 or negative 5 to make it a function.
Right. We're graphing 2 functions at the same time. One function maps 0 to 5, the other function maps 0 to negative 5. Is that clear?
Oh, yeah, okay.
Right? Wonderful. Now we could have done it this way instead. We could have said x equals plus or minus y squared minus 25 and found 2 solution functions for x in terms of y if we wanted. So now if y is 0, what's x?
Plus or minus 5.
Plus or minus 5. You see that?
No. You have y squared minus
Oh, I
25.
wrote it backwards. Thank you. 25 minus y squared. So we won't write it that way. We'll just say when x is 5, we'll calculate what we get. So we plug in 5 for x here. So we won't think about it this way. We could think about it this way, and that'd be perfectly fine. I'm going to keep thinking about it this way. And you'll see we get the same thing. So when x is 5, plug in 5 for here, what do we get?
0.
0, so y is 0. When x is negative 5, what do we get?
Also 0.
Negative 5 squared is 25. 25 minus 25 is 0. Square root of 0 is 0. Plus or minus 0 is just 0.
And that's okay because it's 2 different zeros.
2 different zeros.
Okay.
So 5, 0, negative 5, 0. So this point's on there, and this point's on there. Right?
Okay.
Let's try one more. Let's see, what will be a point that comes out nice?
3.
3 will come out nice? Yes. Okay, so let's plug in 3 for x. What do we get?
What did you plug in for x?
Sorry, x is 3. So what's 3 squared?
9.
25 minus 9.
16.
Square root of 16.
4.
So we got plus or minus 4. So at 3, there was 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So when we plugged in 3, we got 4 and we got minus 4. And if we plugged in negative 3, we would have also gotten 4 and minus 4, because 3 and negative 3 both give us the same thing, right?
Yep.
And we can keep going on with this and plotting all the points, and we notice that we get a circle. Which isn't surprising. X squared plus y squared equals 25. You can think about that as your Pythagorean theorem. It's all your x, y such that their distance is 5 from the origin.
And the theorem for the triangles will help you get a circle. That makes sense.
Yeah, so pick any point on here, create a right triangle. This distance right here is 5. This distance right here is x. This distance right here is y. The Pythagorean theorem says x squared plus y squared is equal to 5 squared, 25. So every point 5 units from the origin is satisfied by this equation. Does that make sense? So this is the equation of a circle with radius 5. Good? And notice that a circle can be, for we were talking about the vertical line test. You can think about it as we have this function, the top half of the circle. That's what you get from y equals positive, the square root of 25 minus x squared. And then we have the function for the bottom half of the circle, which is given by y equals negative the square root of 25 minus x squared. So that's what those are giving us. That make sense?
Oh, it's dude. Okay.
What?
Never mind.
Sound like you had something very important to say.
Something just clicked.
Something just clicked. That's good. A few more of those and we'll learn algebra. Okay. Squiggly line, so we got to here. Okay. So now let's talk about lines for a second. Now you know from geometry that we need how many points to define a line? 2. So pick any 2 random points in existence. This point right here, I'm going to call it x1, y1, and this point x2, y2. Those are just 2 random points. We know nothing about those points. You with me so far? Now, I'm going to plot those 2 points, and then I'm going to draw a line through those 2 points, some line L, here it is, through those 2 points. So I pick any 2 random points in existence, and then I drew a line L through those 2 points. You with me? Now I'm going to pick some other point x comma y on that line. What do I know about that other point? It's going to be between those 2 points, but what algebraically do I know about that line, about that point? What expression is it going to satisfy? We're going to basically come up with our equations for lines. You know how you're used to like y equals mx plus b? We're going to derive that right now. Stuff like that. So any point on this line, what do I know about it? So I'm picking some random point on the line, and I know, ultimately, you know it's going to satisfy some equation, right? I told you if you have some equation and graph it, it gives you a line. Now, we're going to show you that if you have any line, then a point on that line is going to satisfy some equation. And we're going to come up with the equations it's going to satisfy.
Some linear equation.
And it turns out it's going to be a linear equation.
Surprise, surprise.
Surprise, surprise. Way to give it away. Spoilers.
Sorry, my word.
All right, so let's just think about what we know about this point. So I give you these 2 points. These 2 points are given. What do we know about that line? Or about this point, if it's on the same line?
It follows the same equation.
Well, it follows the same equation, but just geometrically, what do you know about it?
Just in the middle, kind of.
It's maybe. I could have grabbed it right here. I could have grabbed it right here. All we know is x, y is on that line.
It's on the line.
We know it's on the line.
No, there's 2 other points on the line.
Okay.
There's infinite points. What are you looking for?
Stuff from what we talked about last time.
We're asking the wrong.
Points on the same line. Yeah, you guys are wrong. We know that the slope between this point and this point has to be the same as the slope between this point and this point.
That's smart.
Right? We talked about that for collinear points last time. 3 points on the same line have to satisfy that slope. So what is the slope between this line and this line? Let's look at that really quick. The slope between this line and this line is just rise over run, right? So what is the rise? What's this distance right here?
Y minus y1.
Y minus y1, good. And what's the run?
X minus x1.
X minus x1, perfect. So this right here is the slope between these 2 points. And that has to be equal to the slope between this point and this point.
Yes.
Right?
Yeah.
So what is the slope between this point and this point? What's the height? So now we're looking at this triangle going from here to here. So what's the rise?
Y squared minus y1. Or y2.
Y2 minus y1 over x2 minus x1. Right? So I know that those ratios are equal. Now I'm just going to multiply both sides by x minus x1 to go from here to here. Multiply both sides by x minus x1. That gets me from here to here. All right. This right here is the equation of a line through those 2 points. And it has its special name, whatever its special name is. I can't remember.
Point slope formula.
No, that's not point slope because it's 2 points. So it's going to be like 2-point formula or something like that. We'll do point slope formula next. If I can even find it. It's just called the 2-point formula. All right. So here's your 2-point formula from algebra. And that's where it comes from. Pretty simple to derive, right? So you should now always know how to come up with the equation of a line. It's pretty simple. Here's the equation of a line. It does look simple, right? Okay. So notice what we did. We knew that the line went through 2 points. And then we grabbed any other random point on the line. For any other random point on the line that we grab, x comma y, it has to satisfy this. So it has to satisfy this. So every point on the line, x, y, satisfies this equation. So the points on the line are solutions to this equation. All right, so when you get solutions to this equation, you get points on this line. Okay, now, sometimes we have a variable for y2 minus y1 over x2 minus x1. What is y2 over y1 minus x2, or y2 minus y1 over x2 minus x1? That's the slope. Sometimes we just replace the slope with the variable m. So going from here to here, just replace your slope with, or replace that with m, and I get you this equation of the line, which is called the point slope formula.
Oh, that's cool.
Good?
I was right.
No, this is the point slope formula.
That's the 2-point formula.
This is a 2-point formula. Do they give you the exact same thing? Yes, every equation of a line does. They all give you the equation of a line. Okay, now let's say that you know that your line happens to cross the x-axis at A and the y-axis at B. You with me?
Yep.
Then, what's the equation of the line? Anyone know that one off the top of their head?
What? It's negative A over B.
Okay, he's just throwing stuff out there.
No, that's rise over run. Negative A over B.
Alright, we'll derive it. We'll derive it if you don't already know. So we're going to use this equation to derive it.
Okay.
Because I know, what are my 2 points? I know it goes through the point 0, comma B, and I know it goes through the point
Oh, you're talking about y?
A, comma 0. Huh?
Is this y equals x supposed to be?
No. This is when you know both its intercepts. And so it's the point-intercept form. Okay. So we'll come up with the equation for it really quick. So using this formula right here, we know that y minus, should we say that this is our first point or this?
A.
This is our first point. All right, so y minus y1 is equal to y2 minus y1 over x2 minus x1 times x minus x1. Maybe I should have written up here b minus 0. Maybe that will help. So I just am using this formula right here for our 2 points. You with me so far?
Yep.
Okay, let's simplify really quick. So this is y equals negative b over a times x minus a.
Alright.
Divide both sides by b and distribute through the a. So this, I'm going to rewrite the coordinates over here just out of the way. This was a comma 0 for that point. Okay, I'm going to divide both sides by b. So when we divide this side by b, that just cancels out the b. When we divide this side by b, we get y over b. Y over b is equal to, now distribute through the negative a. We get negative x over a plus, when we have negative 1 over a times negative a, we get 1. With me?
Oh, yeah.
Let me just rewrite it over here where we have clean space, so that we're not skipping anything. Y is equal to negative b over a times x minus a. Alright, what are we going to do? Divide both sides by b. So we get y over b is equal to negative 1 over a times x minus a. Okay, distribute this through to that. So we get y over b is equal to negative x over a. Negative 1 over a times negative a is going to be plus 1. Okay, now move this to the other side, and so we get y over b or plus x over a is equal to 1. And that is our point-intercept form. So if you know the two places where your line crosses in the equation of the line is y over b plus x over a equals 1.
Yep.
Make sense? Okay, now finally, let's say you know that your line crosses at some point B, and you know your line has some slope m. Now we'll come up with your favorite equation. So we start with this equation right here, and I know that y minus y1, or b, is equal to m times x minus, what's x1? 0. Because the point I'm plugging in right here, this point is 0 comma b. Here's y1, or here's x1, here's y1. So y minus y1 is equal to m x minus x1. Or in other words, y minus b is equal to mx. Or in other words, y is equal to mx plus b. So there's another useful equation for a line. Y equals mx plus b. And for whatever reason, this seems to be all the kids' favorite.
I wonder why. What happens if you solve that third one for y? It gets solved for y.
This one,
Yeah.
you can multiply through by b and move that to the other side, that's fine. It's just this is the way it's typically written, because then it becomes obvious where it crosses, and so you can graph it really quick. If you were to say, graph the line, y over 4 plus x over 9 is equal to 1, I don't need to mess with that at all, I can instantly do it. I go over here up 4, I go over here over 9, I draw my line through those 2 points, and that's the equation of the line.
Okay.
It goes through 4 and 9.
Oh, yeah.
Now you could, if you want that, solve that for y equals mx plus b, plot the b-intercept, find the slope, plot another point, draw your line through it. Fine. But which of these equations is the best depends on your use case. So just depends on what's useful. Okay, so a bunch of different equations for a line. Any questions on any of those equations? All pretty straightforward? Really, all you really need to know is this one. And the rest kind of come for free. Or all you really need to know is this ratio. And everything comes for free. It all comes from that ratio.
I mean, really, you just need to know the picture.
Well, pictures can lie. Don't trust pictures. Trust ratios, though. So, ratios of collinear points are equal. That's what all that comes from. Okay. So now, let's do a bunch of examples. Our job is to graph lines. I think. No, our job is to come up with equations for lines. And that's what I think we're supposed to do in each of these examples. So example 1 is find the equation of a line that passes through the point 2, 3 and negative 3, 5. So we know that it passes through 2, 3. I'm just going to draw really rough pictures to help us get a feel for it. And negative 3, 5. Negative 3, 5. Something like this. Roughly.
Isn't 5 up?
Yeah, 5 is up. That's some quick thinking. Alright. And negative 3, somewhere like that, 5. Thank you. Good correction. So our line looks something like that. So better have a negative slope with whatever we find. Okay, so we're trying to find the equation of the line. We have 2 points. Obviously, we want to use this equation, right?
Obviously.
Obviously, we have 2 points, so we're going to use the 2-point formula. So we have y minus y1 is equal to y2 minus y1 over x2 minus x1 times x minus x1. Did I do that right?
Yeah, y1 equals 5, 2. Joking equals 3.
Huh?
That 5 needs to equal 3.
Thank you. y2 minus y1. x2 minus x1. Okay, are all my numbers good?
Mm-hmm.
Now,
Yeah,
this one is supposed to be minus
3.
Plus.
I switched which point I called which. Restart.
No.
This is my 1, this is my 2, right?
Yes.
So my y, I should have y minus y1, 3,
Yes.
is equal to y2 minus y1 over x2 minus x1 times x minus x1. There we go. Alright, so now we just simplify. Y minus 3 is equal to 5 minus 3 is 2, negative 3 minus negative 2 is
Negative 5.
negative 5. So we have negative 2/5, which we were hoping for a negative slope, right? So that makes sense. Times x, we can distribute that through. Negative 2/5 times negative 2 gives me plus 4/5. And then, if you want to move the negative 3 to that side, we can. So then we get y is equal to negative 2/5 x
Plus 19.
plus 19/5. Good. Which, that makes sense with the picture we drew roughly, right?
Good.
Okay, so let's do the next one. We know that it goes through the point 2 and has a slope, point 2, negative 5, and has a slope of 3. So let's get some intuition for that. 1, 2, 1, 2, 3, 4, 5, 2, negative 5, and then has a slope of 3. So if you go up 3 over 1, geez, that's terrible. But roughly, that's what it looks like. So our y-intercept is going to be pretty far down there when it's all said and done, right? So that's roughly what our picture looks like. So that's just helping us with sanity checks to make sure we don't make mistakes. So now we're going to use the point slope formula. So we have y minus y1 is equal to m is equal to mx minus x1. So we have y plus 5 is equal to 3x minus 6. So we have y is equal to 3x minus 11, which is what we were expecting. Steep line with a pretty low y-intercept. Okay? X-intercept at 3, y-intercept at negative 5. Oh, skip this one. So this one we have, remember this is our one. We have y minus y1 is equal to y2 minus y1 over x2 minus x1 times x minus x1. Okay, what's our slope on that line going to be?
It's undefined.
Son of a gun. How are we going to do this thing? Our formula is broken.
Why is that?
It's trying to force us to divide by 0.
Oh, I thought that was why.
Those are both 3's. 3 minus 3. Why is our formula broken?
0, 0.
Because this is a vertical line.
Because it's a vertical line.
Oh, because, yeah, it's not a function.
Yeah, this is what happens when we don't draw our picture first. 1, 2, 3. We have 3, negative 5, that's somewhere down here. 3, negative 8, that's somewhere down here. It's straight up. By definition, vertical lines don't have slopes.
Those are linear equation.
It is a linear equation. What's the equation? The equation is y equals, or x equals 3. Okay? So that was supposed to be a gotcha.
Well, it wrong.
That's good. Alright. Next we have x-intercept at 3, y-intercept at negative 5. So our line looks roughly like that. What's the equation of our line?
Y over B y x over A equals 1.
Yeah, so we can just write this as y over negative 5 plus x over 3 is equal to 1.
Why does B and A equal those intercepts? Definition of A.
That's coming from this right here. And so now, if you want, we can multiply both sides by negative 15,
Mm-hmm.
right? Multiply both sides by negative 15, what do we get?
Y plus x over equals 2
Er.
negative 15.
Yeah, so we're going to get, right here. We got 3y minus 5x is equal to minus 15.
Mhm.
Sorry, we won't multiply through by 15. We'll just multiply through by negative 5. I'm just trying to get at how you guys might want it.
Mhm.
So multiplying through by negative 5, then we get y minus 5/3 x is equal to negative 5. Or we get y is equal to 5/3 x minus 5. Right?
Mhm.
Now notice, this definitely has a positive slope. And this is also kind of obvious using our point slope formula. We could have just written it this way if we wanted. We have y is equal to, what's our slope? Well, by the time we go up 5, we go over 3. And then what's our y-intercept? Minus 5. Same thing.
Yeah. Yeah.
Good? So, shouldn't matter which equation you use. They should all give you the same thing. It's just a matter of whatever you like. All right. We're supposed to find, in this case, oh no, we're here. Slope of 3, y-intercept of 5. Well, we already know what that is. That's y equals 3x plus 5.
Yeah.
And no point drawing that one out. I think you guys already get those. Find the slope-intercept form if I know that 3x plus 2y minus 8 is equal to 0. So I'm going to move the 8 to the other side and divide everything by 2 as I go. Well, maybe I won't do all that in one go. I'll just move 8 to the other side and write my y first. So we have 2y plus 3x is equal to 8, right? Divide through by 2, and we get y plus 3/2 x is equal to 4. Or we get y is equal to negative 3/2 x plus 4. And there's the slope y-intercept form, or slope-intercept form. Okay. Sorry, what?
Say that again.
We started with this expression, and we were supposed to rewrite it in the slope-intercept form, which is this way. That was our job in that example.
Yeah, I think I can do the top one.
Okay. Now, quick proof that the graph of any linear equation is a line. So take any linear equation, ax plus by plus c equal to 0. We're going to prove that that's always a line. Ready? So, proof ax plus by plus c equal to 0 is a line. Now we have two cases. We have the case where b isn't equal to 0 and the case where b is equal to 0. So 1, if b is not equal to 0, then we can rewrite this as, we can say by is equal to minus ax minus c, moving ax and c to the other side, right? And then we can say y is equal to negative a over bx minus c over b. Since b is not equal to 0, our division we're guaranteed is good and we're not adding or removing solutions. And we know that this is the equation of a line with this for a slope and this for a y-intercept. Right? So we just barely showed, if b is not equal to 0, this definitely gives us a line. 2, if b does equal 0, then we have, just solving for x, we get x is equal to negative c over a, which is a vertical line through negative c over a, which is a vertical line. Therefore, any equation of this form that you give me is for sure a line. Good? Now, to prove the converse of that, I don't think we really need to write it out. It's pretty self-explanatory. But to prove the converse of that any line has one of these equations backing it. How do we do that? We pick a line and we have one of two cases. If you pick a vertical line has to pass the x-axis somewhere, so it has to cross at some point A, and so it's represented by x equals to A. Right?
Okay.
If you pick a non-vertical line, then we know that every line that's not vertical has a slope. So then it has to have a slope, which we call m, and it has to cross a y-axis at some point b, and then we know its equation is y equals mx plus b. So we prove that every linear equation represents a line, and we prove that every line represents a linear equation. So there's a one-to-one relationship between linear equations and lines. Make sense? Okay. And that's kind of the big takeaway of everything we were doing today. Let's do this last one because it, this example references something from that we did at the end of last class. More tricky problem. So we're supposed to find the equation of a line that goes through negative 2, 3 and is perpendicular to the line 3x minus 4y equals 5. So let's get some intuition for this. First off, let's figure out this line really quick. So we'll put down here. This is 3x minus 4y is equal to 5. Solving for y, I'm going to move y to the other side and 5 to this side, but write it in backwards order. So moving the y to the other side gives us 4y is equal to 3x, and then we move the 5 to the other side, minus 5. You follow that?
Yeah.
I moved the 4y over here, and I moved the 5 over here, and then wrote them backwards. Okay, solve for y, and we get y is equal to 3/4 x minus 5. Force. Alright, let's get a rough feel for this equation. We won't be too perfect about it. So it goes through -5/4. Here's -4/4, so -5/4 is somewhere right there. And it has a slope of 3/4. So by the time it goes up 3, it goes over 4, so something like that. Real rough. Right? Now our job is to find the equation of the line that goes through the point -2, 3. So -2, 3. And is perpendicular to this line. So we're finding the equation of the line goes through this point and is perpendicular to this line. So perpendicular to this line means it looks something like this. Again, my picture is probably lined a lot. You with me? Okay. So for our line, what is our slope going to be? This is something we proved at the end of last time. -4/3. If this line has a slope of 3/4, then a line perpendicular to it has a slope that is a negative reciprocal. So 3/4 is the slope of this line. The reciprocal of 3/4 is 4/3. The negative reciprocal is -4/3. So if this line has a slope of 4/3, its perpendicular line has a slope of -4/3. If this line had a slope of 2, which would be shooting up like that, its perpendicular would have a slope of -1/2. Okay? So we know that our slope is -4/3, and we know a point that we go through is -2, 3. So we know our slope, we know a point, we can use our point slope form, which is this one. So the equation of this line right here is going to be given by y minus y1 is equal to m, -4/3, times x minus x1. What did I do? -2, 3 is over here. -2, 1, 2, 3. So we were talking about this line. Okay? Alright, and I drew it bad. Its y-intercept is probably going to be more up here. It's probably going to have a positive y-intercept. I drew that slanted down too much. Okay, so this is a point -2, 3. Did that way too many times today. Alright, so y minus y1 equal to m, that's a minus sign, -4/3, x minus x1. Okay. So, since I don't like keep writing up there, we'll just start doing the algebra down here. So distribute through the -4/3 and we get y is equal to -4/3 x minus 8/3, and then moving the 3 to the other side gives me +3. You follow everything I did there? I distribute through the -4/3 and move the 3 to the other side. Good? Alright, so that's y is equal to -4/3 x. If we have -8/3 and we add 3, then we're left with
1/3.
1/3. Negative 8/3 plus 9/3 leaves me plus 1/3. Like I said, it should probably cross right there. I didn't draw that very good perpendicular. So better line. More like that. Make sense? Yeah? You're going to need a lot of this for tomorrow. Just warning you. Doing a lot of algebra tomorrow. A lot of stuff with lines. Fortunately, that's all we're doing. As far as lecture-wise. Anyways. So there's that. Last thing to notice. Parallel or coincident lines. So let's say I have two lines. One line, a1x plus b1y plus c1 equals to 0. Some linear equation in terms of x and y. And I have some other linear equation in terms of x and y. So we have two lines right here, right? I'm going to solve them both for y. So move this to the other side, move those to the other side, and then divide by b1. So when we move that to the other side, it becomes negative. When we move that to the other side, it becomes negative, and then divide them both by b1. That's solving for y. You see how I went from here to here?
Yep.
And then it's identical going from here to here. Exact same thing. Just changes the subscripts.
Did you mean for that D2 to be a B2?
I sure did. D2's nowhere on the board. Thank you. All right, no more mistakes. Okay, now notice that this is in slope-intercept form, right? So what's the slope of this line?
A1 over B1.
Negative a1 over b1.
Yeah.
And what's the slope of this line?
A2 over B2.
Negative a2 over b2.
Oh, it's on the A.
Oh, yeah, sorry. So, two lines are parallel if and only if they have the same slope. So these two lines are parallel to each other if and only if a1 over b1 is equal to a2 over b2. Let me do a quick sanity check here to make sure you're understanding this. If I have 5x plus 3y minus 17 equals 0, and I have 15x plus 9y plus 21 equals 11, are those two lines parallel?
No. Yes.
Look at a over b, what do you get?
3/5.
A over b,
5/3.
a over b,
15/9.
which is
5/3. Because you take out the 3.
5/3. Are those the same?
Pretty much.
5/3 is 5/3. So these two lines, whatever they are parallel. You with me?
Oh, yeah.
Okay, there we go. The c is different, which is going to change its y-intercept. But these two lines are parallel. So if a1 over b1 is equal to a2 over b2, the lines are parallel. And if on top of that, c1 over b1 is equal to c2 over b2, then the lines are identical, or in other words, the two lines coincide.
Assuming they're parallel.
Yeah, if they're parallel, and they have the same y-intercept, then they're the same line. They coincide with each other.
What are the double lines on the left?
Parallel.
Oh.
Sorry. I read it out loud, I just squish it so I can fit as much as possible. So parallel if and only if they have the same slope, and then they also coincide if and only if they have the same y-intercept. So if they have the same slope and they have the same y-intercept, same line, they coincide. If they just have the same slope, then they're parallel. Make sense? That's what I meant for that to say. Okay, so that's all we have for today. We'll end it there. And since more people ended up showing up, then I guess we'll continue with the class.
Do we have to quit it?
We were possibly going to switch it up because it was just these two last time. If it was just those two, may as well, if they didn't want to do this, do something else. So
Why would you do a class with just 2 people in it?
yeah, what a waste of time, right?